don't know if this is a good category name, liquid in a shape problems, but what's going to be happening is we're going to be pouring liquid into different shapes, and as you do that, you're going to look at rates of change. So in this case, we've got a trough. Have you ever heard of the word trough before? So it's 10 feet long, and the ends are isosceles triangles. So the first thing that you kind of have to be somewhat good at in this unit is being able to visualize and draw what you just read. So we've got an isosceles triangle, 10 feet long. Whoa, there we go. There's our trough. It's getting filled with water. So what do we know about this trough? We know this is 10 feet long. The ends are isosceles. It has an altitude. Have you heard the word altitude before with triangles? Altitude is another word for height. So we know that this height in here is 3, and the base is going to be 4. And the vertices are on the bottom, so this is what your trough looks like. So if water is poured into that trough at a rate of 3 cubic feet per minute, how fast is the water rising when the water is 1 foot deep? So we're trying to find how fast the water is rising. That would be dh dt, change in height. That means that our height is a function of time. We know that the water is being poured at a rate of 3 cubic feet per minute, so we know how much the volume is changing with respect to time. 3 cubic feet per minute, and that means volume is also a function of time. We want to find it specifically when the height is equal to 1. So as far as following things that we've done up till now, we start by setting up what we know. This is sort of setting up what we know and what we want to find. We want to find dh dt. We know that both of those are a function of time, and then we wrote out a formula that related the volume and the height and different things like that. So when I start to write out the formula here, first of all, we've got our trough is a triangular prism. So the formula for the volume of that, same kind of idea that we used for a formula for the volume of a cylinder. Remember the cylinder, I said you could cut out a piece of paper that's in the shape of a circle and then just keep stacking those circles up until you filled the whole thing. The same concept is going to happen here with our triangular prism. But now you cut out a piece of paper that's in the shape of a triangle and keep stacking that up until it would fill the whole thing. So as far as creating that formula, well, it's going to be the area of your triangle, which is base times height divided by 2, times by the length of your triangle. In this case, our length is always 10. Now, the reason I didn't put in values for base and height, even though we've got the base of our triangle is 4 and our height is 3, well, we don't know if the trough is completely full. In fact, we're trying to find out how fast it's rising when the water level is right there at 1 foot high. So the 10, the length of 10 will always stay the same, but the base and the height are going to be changing. I'm going to draw just the triangle with the base and the height listed there. Because in order to take our derivative, in order to find dh dt, right now you see in our formula we have 3 variables. So one of the things that we're going to have to try and do is see, is there a relationship between the base and the height so that we can write this equation just with h as the variable? Well, as the water is rising, this is always the triangle that gets made. When that triangle, when the trough is completely full, then the height would be 3 and the base would be 4. Now some things about these triangles. And this is what's going to happen in a lot of questions, and we're going to get triangles that are similar. Does it make sense that these two triangles will be the same shape always? That no matter what, this angle at the bottom is the same as this angle because it's the same trough. And when you go straight across, this angle is always going to be the same as this angle. So because they're similar triangles, their lengths are always going to be proportionate to each other. So as far as setting up a proportion, and I can set this up as, for example, if I take the base divided by the height as a proportion, it has to be the same as the base divided by the height of the triangle when it's full. Rearranging this formula and solving for the base, I get that the base is always 4/3 of the height. So this question has a little bit extra work because once you write out your formula, you find out you have more variables than you want, because we weren't given any information about how fast the base was changing with respect to time. So we needed to work at changing this formula so that it only has height. 10 divided by 2 is 5. Multiplying that 5 through, we're going to get 20h squared over 3 as our equation of volume in terms of h only. And now we can do implicit differentiation. I'm just going to show that by saying I'm going to take d dt of this whole thing. That's going to give me dv dt equals 40h over 3 dh dt. Yes. The 20 and the 3 are our number in front, right? So when this 2 comes out in front, it's like 2 over 1, and it'll multiply 2 times 20 to get 40, and the 1 times 3 to get 3. And so if we want to find out how fast the height is changing, how fast the height is changing with respect to time when the height is 1, we know that dv dt from the original question was 3. We're going to plug in 1 for the height. And solving for dh dt, we get 9 over 40. Putting that with units, 9 over 40 is, our height was measured in feet per minute. So when the depth is 1 foot, the height is changing at 9/40 feet per minute. That's hard to say. If you want to change that to a decimal, 0.225. So it's changing at 0.225 feet per minute when the depth is 1 foot. Okay, I'm going to get you guys to try this one on your own. I'll come around and help you with formulas if you can't remember them. Draw a picture to begin with. So there's our cone. Height of 5. and a diameter of 6 meters at the top. That means your radius would be 3. Water is being pumped into the tank at a rate, so we know our volume with respect to time, meaning that volume is a function of time. It's 1.6 meters cubed per minute. We want to find the rate at which it's rising, so we're trying to find dH dt when the height is 2 meters. So that tells us that height is also a function of time. Go to our volume formula for a cone, and pi r squared times height, which is a cylinder, divided by 3 to make our cone. Now, our formula has radius and it has height. But as far as the information that we have at the top, we don't have any dr dt, and we don't have at a certain point what's the radius. So one thing to look at is their relationship between the radius and the height. So if you had a specific height that you didn't know as part of that cone, can you see when that water level rises in here that your radius and your height always make a triangle? And this angle of that triangle is always the same. So again, we have similar triangles, and we can do ratios. So that means the ratio of the radius to the height, well, if we look at our complete triangle at the top, the radius is 3 and the height is 5. That ratio has to stay. As far as getting r all by itself, we find out that our radius is always height. So now we can plug that back in to our formula. The radius gets squared, so that 3/5 times height gets squared, times height divided by 3. Just simplifying this a bit, you're going to get 9 over 25 times pi times h cubed all over 3. Which will give us 3 over 25 pi h cubed. So now we are able to write our equation just in terms of height. So if we take the derivative with respect to time of this whole thing, yes, I can go back up. Is that enough? Okay, I'll wait for you for a second. Just tell me when I can scroll back to where we were. Now we can plug things in that we know. We know that dV dt was it 1.6? We're trying to find it when the height was 2. So height squared will be 4 dH dt. So as far as multiplying these things, I'm going to do a little bit of mental math here. Are you okay with changing 1.6 to a fraction, 8 over 5? And then here we're going to get 36 pi over 25 dH dt. Multiply both sides by 25 and divide both sides by 36. And we are going to get 20 over 9 pi dH dt. If you simplify it, I multiply both sides by 25. So that's going to cancel out, leave a 5 on the top. Divided both sides by 36 pi. And the 36 and the 8 will leave me a 4 and 9 when I simplify. And so 5 times 4 is 20, and then I've got left with 9 pi on the bottom. If we figure this out as an actual value, get 0.707. So we know that our height is changing at 0.707 meters per, as far as we need to write a statement here at the end. What was our unit, seconds or minutes? Minutes. At 2 meters, that's how fast the height is changing.